Okay, so today I want to keep teaching you about cryptography. Yeah, we're doing a lot of cryptography in this class. And what I want to teach you about today is public key cryptography. So we're going to look at how to make symmetric key cryptography practical. We talked previously about how to encrypt if Alice and Bob have a shared key, but also it's kind of not realistic for them to have a shared key. So where we're heading is trying to eliminate this requirement for them to have a shared key. And last week, I showed you Diffie-Hellman key exchange, which is a way for Alice and Bob to share a key so that they can then encrypt or use the message authentication code. Does anyone remember what were the disadvantages of Diffie-Hellman? What were the downsides or the limitations of Diffie-Hellman key exchange? Yeah?
Or Bob for really giving their keys to like that person's mouth.
Totally. Yes, exactly. If there's an interceptor, Mallory, who is like intercepting messages and changing them and replacing them with other messages, then Alice can end up sharing a key with Mallory, not with Bob. We often call that a man-in-the-middle attack, because Mallory somehow like sits in between Alice and Bob, and to Alice pretends to be Bob, and to Bob pretends to be Alice. Okay, so that's one problem. It's not secure if there's a Mallory present who's changing messages. Any other limitations? Shortcomings? Weaknesses? Okay, that's the main one. I buy that. That's the main one. Not secure against man-in-the-middle attacks or against active attacks. Also, another limitation is that both Alice and Bob have to be online and internet connected at the time when they want to exchange the key. Not that big a deal, but they do have to be able to communicate with each other and send messages back and forth. So for instance, if I'm sitting on an airplane and I want to send an encrypted message to my friend, but I didn't buy the Wi-Fi access on the plane, then I can't use Diffie-Hellman to share a shared key, and so I can't encrypt the message while I don't have internet connectivity. Maybe not that big a deal. Lastly, it's kind of connected to the same thing that you said. It's kind of another way of viewing this problem, the man-in-the-middle problem. It doesn't provide authenticity. There's no way for Alice to verify it's Bob she's talking to as opposed to Mallory. Okay, so what I'm going to show you now is some way to try to get the same advantages, but to deal with those limitations, solutions for those limitations. So we really truly have a solution that will let us encrypt and authenticate messages with other people we want to communicate with. And the tools we're going to use, public key cryptography, are also called asymmetric cryptography. So that's what I want to teach you about. I want to teach you about public key cryptography. And in this roadmap that we set up, we're on the right half of the table. So I'm going to start at the upper right part. So I'm going to start with encryption. And then we're going to get to some public key signature schemes. So this is kind of the analog of like encryption with a block cipher or a message authentication code, but we're going to look at a version of that that doesn't require a shared key. So in public key cryptography, rather than having a shared key, there's going to be two keys. Each person is going to have two keys. Alice is going to have a public key and Alice is going to have a private key. The public key is called public because she shares it with everyone. That's like her business card or like her email address. That's the information needed to send a message to her. Then she has a private key, which she doesn't tell anyone, not even Bob, no one. That's only she knows her private key. And in encryption, anyone's going to be able to encrypt a message to Alice using her public key, but only she can decrypt with the private key. So now we have every key has like a counterpart. The public key has a private key that corresponds to it, and the private key has a public part that corresponds to it. And to construct these now, we're going to need some fancy math, number theory, all sorts of stuff. And I'm not going to try to teach you all the number theory. I'll give you a sense of how they work, but it's like a deep and rich area that with like lots of mathematics. The benefit is Alice and Bob are going to be able to communicate without having to have shared a secret in advance. So much more practical. And the drawback is it's slower. All right, so the first form of public key cryptography is encryption. And encryption is about keeping messages confidential. We previously saw how Alice and Bob can communicate confidentially if they have a shared key, but now we're going to look at what if they don't. So the idea is like Alice has, I don't know, a love letter to send to Bob, where she, sends some my Wookie pumpkin or something like that, whatever her cute, pet name for Bob is, that she doesn't want anyone else to see because it's, oh my gosh, so embarrassing. And she's going to encrypt that with Bob's public key. And then Eve, the eavesdropper, is not going to be able to decrypt it. The only one who's going to be able to decrypt is the person who knows the private key that corresponds to the public key she encrypted with. So if she encrypts with Bob's public key, the only person who'll be able to decrypt is someone who knows Bob's private key. And Bob doesn't tell anyone else his private key, so only Bob will be able to decrypt. That's the concept. So this algorithm is going to have three like algorithms or three operations. The first is we need a way to generate a key pair, a matching pair of public key and private key. And then we're going to need a way to encrypt a message with the public key, and we're going to need a way to decrypt a ciphertext using a private key. So I'm going to write PK for public key and SK for private key. Public and private start with the same letter, so you need it. So S, secret. And what we want from the scheme is obviously you should be able to decrypt any encrypted message and get back what you started with if you know the right keys. And we're going to want a notion of security, which is going to be basically the same thing we saw for symmetric key encryption. This in CPA game where if Eve knows that one of two messages was encrypted and she sees a ciphertext, she can't guess which of the two messages was encrypted with better than 50% chance. Okay. In CS70, you might have been shown RSA encryption. So I'm going to show you a different one, El-Gamal encryption. But RSA encryption and El-Gamal encryption are two schemes for public key encryption. Okay, so in this upper right-hand block, we're in the confidentiality encryption at the top and public key or asymmetric key on the right. And El-Gamal is kind of starts from Diffie-Hellman key exchange. Diffie-Hellman key exchange was invented first in the 1970s, and then maybe 5 years or 10 years later, El-Gamal encryption was invented. To solve some of the limitations of Diffie-Hellman key exchange. And Diffie-Hellman is great because it allows Alice and Bob to come up with a shared symmetric key. But it doesn't in and of itself provide a way to encrypt messages. So El-Gamal is going to extend Diffie-Hellman so that we can directly encrypt messages. And the idea is really, really simple. It's kind of boring. It's like Diffie-Hellman plus one-time pad equals El-Gamal. So do you want to try sketching out or taking a guess how that might work? Suppose that you know how to do Diffie-Hellman to get a shared secret, this G to the AB mod P. If Alice wanted to encrypt a message, how could she encrypt a message? Given that they've exchanged this shared secret and given what I just said. Yeah?
Exchange which you it's a pad as your diffie-Hellman template.
Yeah, I can treat this shared secret, G to the AB mod P, as a pad. And then Alice could encrypt her message M with like one-time pad with that as the pad. It's not exactly one-time pad because one-time pad says your pad should be truly random, and here this shared secret's not truly random, it's generated in a systematic way, but we can do the same kind of scheme. It's kind of like one-time pad, kind of like a stream cipher. How should I get the ciphertext from the message and this pad? How do I combine the message and the pad to get the ciphertext? XOR. Why XOR? Why is XOR good? Can you remind me? Because you can undo it. Exactly. Great. Great. So XOR the two. Perfect. And we'll have to make sure that the message is not any longer than the pad, right? So however long the pad is, that sort of puts a maximum on the length of the message, and then just XOR the two. Do I have to do XOR? Is XOR the only operation or is there any other operations I could do that would also work? Yeah? Totally. You could use an encryption algorithm like AES. Yeah, encrypt AES with CBC mode. What would you use as your key for the AES encryption? Whatever you shared. Exactly. Perfect. Yes. Okay, we got two options, XOR or AES encryption. Any other operations we could do to combine the message and the pad? And a big hint is you said what's good about XOR? It's reversible. You can undo it. Are there any other operations, any other way of combining two quantities that you could undo? Like here we're working Diffie-Hellman work modulo P. XOR is not really a modulo P operation. Is there any modulo P operation that is undoable in some sense? Add it. How about adding it? Adding it. So what if we added the message and the pad and use that as our ciphertext? Would that work? Is it reversible? Can Bob decrypt when he gets this? Yeah, he should be able to. Bob knows the G to the AB, so how does he get from the ciphertext? How does he get back to the message? Add in that shared secret. Subtract it. You got to subtract it, right? Bob would take the ciphertext and subtract the shared secret, and he'd get back the message. So addition is also sort of reversible or undoable. A little tricky detail is you don't want to actually use addition. You want to use addition modulo P. So it like wraps around. Why is that? Explaining why that is tricky. Do you care? Do you care why? Or do you just want to take it on faith? Take it on faith? Okay, I'm going to let you, if you care why, I'm going to let you ask. But so so we've got three operations now. XOR, you undo that by XORing again. AES encryption, you undo that by AES decryption. Or add mod P, you undo that by subtract mod P. Now, El Gamal basically says, let's just do that. Except for whatever reason, it doesn't use any of those three operations. All three of those would work. They all would be fine. But for some reason I can't explain, it chooses a fourth operation that is also undoable. And it's a mod P operation. And for some reason it didn't like add, and so it used multiply. Don't ask me why. I don't know why. Any of those four would be fine, but the standard El Gamal uses multiply. So that's what I'm going to teach you. I'm going to teach you the standard one that you'll find in every like textbook and technical standard and so on. So El Gamal encryption now is this big beast of a thing. But don't get overwhelmed. It's not so bad. It's not so scary as it looks. What happens is Alice and Bob do a Diffie-Hellman key exchange. The result of the Diffie-Hellman key exchange is they end up with G to the AB mod P. They end up with the same value. And then to encrypt, the ciphertext is this C2 value. To encrypt, what Alice does is she takes her message M, multiplies that by that shared secret value mod P. This is in place of XOR, multiply mod P. And then to decrypt, Bob gets that C2 value. And to decrypt, how should you undo the multiply? You could shout it out. It's okay if you're wrong. Divide. How do you undo multiply? Divide. And in modular P arithmetic, we want to divide by that shared secret. The way you divide by something in modular arithmetic is you multiply by the inverse. So what the recipient, Bob, does is he computes the inverse of the shared secret and he multiplies by that. So Alice multiplied by the shared secret. Bob multiplies by the inverse of the shared secret. Shared secret times its inverse equals 1. So what Bob's going to get back is the original message. Basically, Bob divides by the shared secret. Except this division is a mod P division. It's not a normal division. So that's the basic idea. It's Diffie-Hellman, and then do one-time pad, but with multiply instead of XOR. But there's actually a little bit more going on here. The other thing that's going on here is, if you look at this slide, there's no point in this slide where I say Bob sends to Alice something. But in the Diffie-Hellman key exchange, there is a point in the Diffie-Hellman key exchange where Bob sends Alice G to the B mod P. So there's another tweak that this guy El Gamal, who invented this, did to Diffie-Hellman, which is this very clever idea, the second idea, to make it so that Alice and Bob don't have to be online together at the same time. The idea that El Gamal came up with is Bob in advance picks his exponent B, computes G to the B mod P. Diffie-Hellman says, send that to Alice. But in this scheme, Bob is going to do that once and call that his public key. Give that to anyone who wants to send messages to him. Like give it to Alice or anyone else, put it on his business card, put it on his web page, include it in his email signature. So Bob generates G to the P mod P once and sends it, like publishes it to the world. You could think of that as like sending it to Alice, but it doesn't really matter how it gets there. And it might have been sent to Alice long ago. That is the same message that he would have sent in the Diffie-Hellman key exchange, but now we're just calling that his public key. Alice does the same as she would do in a Diffie-Hellman. She picks R and computes G to the R. I called it A before. She would pick A, computes G to the A. Same thing, A or R, same thing. And then the shared secret is obtained, it's G to the RB. Alice can get that by taking the G to the B from Bob and raising it to the rth power. How does Bob get that? Alice has to send Bob something, and the C1 is what Alice would send in a Diffie-Hellman exchange. So the relationship between this and a Diffie-Hellman key exchange, C1 is what Alice would send in the Diffie-Hellman key exchange. Bob's public key is what Bob would send. So you imagine that Alice and Bob do this Diffie-Hellman key exchange, and then the C2 is what the encrypted message. So you imagine Bob sending his part of the Diffie-Hellman, he calls that his public key. Alice sends her part of the Diffie-Hellman, that's C1, and then she sends the encryption of the message. And since she's sending two things, we might as well bundle them together and send them in a single packet. So the ciphertext now we consider to be the combination of these two things that Alice sends. Whoa, okay, this is either like really obvious or like really confusing in all the details. And I don't know how I did in explaining it. So I'm trying to explain to you how we turn this Diffie-Hellman interactive key exchange into a public key encryption algorithm. How we generate a public key, how we encrypt, how we decrypt. How did we do? Are you feeling like, oh, that was obvious? Why did this guy El Gamal get something famous from this? Are you thinking, I have no clue what's going on? Are you thinking, I get it, but my mind is at its maximum capacity? Where are you at? Yeah?
Alice doesn't see any information from Paul that someone else made.
Uh-huh.
There's absolutely nothing preventing someone else giving a message to Bob.
Uh-huh. Yeah, so you're worried about someone else pretending to be Alice or someone else pretending to be Bob?
Bob, no information about Alice.
That's right. Bob has no information about Alice. I like the way you think. You're thinking like a cryptographer. How does Bob know who's sending him this message? He has no way to know. He has no way to know who this encrypted message comes from. It could come from anyone who knows his public key. He shared his public key with the world. He published it. So it could have come from anyone. So this public key encryption gives Bob no information about who sent it to him. Yeah. Yeah, it's different from like AES encryption in that sense. Yeah?
That Bob is able to access that without it being modified.
Got it. Is Alice sending R for the public? So, oh, this is confusing. I have a lowercase r and a capital R on this slide. Yeah. Big R is sent over the insecure channel. So the C1 is big R. C1 and C2 are sent over the insecure channel. So Bob receives it, but also any eavesdropper can also see it. Everything that Alice sends, an eavesdropper could see. And what Alice sends is R and M times capital B to the little r, M times the shared secret.
So it's like, okay, like we're not super worried about someone like messing with that R value.
Got it.
Really,
Good. I like what you're thinking. You want to know what's the implications of sending that over an insecure channel? Could someone observe? Someone could observe it and someone could like try to modify it, right? We don't need to worry about someone observing it because Diffie-Hellman key exchange, security of Diffie-Hellman key exchange says you can observe it and it won't help you learn what the shared secret is. There is the possibility that someone could modify that. That Mallory could modify that. And then if Mallory modified the ciphertext that Alice sent, maybe Bob would receive garbage, or maybe Bob would receive a total other message that was not what Alice wanted to send. Both of those are possible. So if there's a Mallory, we're going to get to that in a moment, but if there's a Mallory, then Mallory could mess with this. She won't learn the message, but she could cause Bob to receive something else. And that kind of is, maybe in retrospect, we should guess that that should be possible because like we just said, Bob has no way to tell who this is coming from. Anyone could encrypt a message to Bob. So Mallory could just discard anything Alice sends. If Mallory can modify Alice's messages, Mallory could just discard everything Alice sent, encrypt her own message and send that instead. Yeah. How are we doing? Other questions, other feedback? I would love you to stop me if I've totally lost you. Yeah. Can I explain Diffie-Hellman again? Yes. Do I have a slide or do I have to go back to a previous slide deck? Here's Diffie-Hellman. In Diffie-Hellman, Alice chooses the secret exponent, lowercase a, and sends g to the a mod p. Bob chooses a secret exponent, lowercase b, and sends g to the b mod p. And then if you work through the math, they can both derive a shared secret, g to the a b mod p. But an eavesdropper who sees what they've sent is not able to derive that shared secret. It's kind of a weird consequence of the way the math works. And it has to do with this discrete log problem. An observer, an eavesdropper who observes G to the A mod P, they just see a number and they can't figure out what A was because that would require solving the discrete log problem or undoing this one-way function. So an eavesdropper can't learn A, can't learn B, can't figure out the shared secret, but both Alice and Bob can compute the shared secret. Elgamal is gonna like kind of do something inspired by that, except Bob's thing that he sends, we're gonna relabel that as Bob's public key. And Alice's thing that she sends, that's gonna be part of the ciphertext for Elgamal encryption. Okay. So an eavesdropper, just the same way that an eavesdropper can't figure out the Diffie-Hellman shared secret, an eavesdropper can't recover what message was sent with Elgamal encryption. What Mallory, an attacker, a man in the middle or an active attacker can do, we've just been discussing this, is replace the ciphertext with some other encryption of some other message. Another thing that Mallory can do is can modify the ciphertext and cause a predictable change to the message that Bob receives. Alice sends C1 and C2. If Mallory keeps C1 the same but multiplies C2 by a factor of 2, doubles C2, then when Bob goes to decrypt, instead of getting back the message M, Bob will get back the message 2M. Double the message that Alice sent. So Bob will have no idea that there'd been any tampering present, and he receives a message that's different than what Alice intended him to receive, what Alice actually sent. So this is an attack that is possible with Elgamal encryption. Elgamal encryption does not prevent this kind of tampering with the message. Elgamal protects the confidentiality of the message, but not the integrity or the authenticity of the message. And a little detail that to actually implement this, I'm only telling you the core idea, but there's actually some other stuff you have to do to implement this for it to actually be truly secure. You got to format the message M appropriately with what's called a padding scheme that adds some redundancy and does some other stuff. Otherwise, there are sneaky little short weaknesses in this thing. Okay, so that's Elgamal encryption. Another public key encryption algorithm is RSA. Yes.
What is the G in, for example, in global roots of like M times G?
Yeah, what is G? G is this fixed constant. Like P is also another fixed constant. P is a prime that is fixed. You can think of it as like someone chose this and everyone in the world uses the same prime P. It's not secret. We just need a prime there so that we're using modular arithmetic. And we need a base, G. So G might be a number like 2 or 3.
But everyone knows that.
Everyone knows it. There's no secret. It's kind of not important what value you choose. You just have to have a value that everyone is using the same thing. Okay, so that's Elgamal encryption. I want to also show you RSA encryption, which is another public key encryption scheme. You can use either. They're both equally good. They both accomplish the same thing. If you understand either of these, you'll probably have an idea, a good understanding of what public key encryption is. So if I lost you in the math for one of these, then you can wake up for the math for the other one. Okay, so how does RSA encryption work? RSA encryption works a little differently, but it's also using number theory and prime numbers. In RSA encryption, we're going to have 2 prime numbers, P and Q, but this time they're going to be secret. Each person is going to have different prime numbers of their own. So Alice is going to have a P and Q, and Bob is going to have a different P and Q. And Alice is going to keep her P and Q secret. That's her private key. Part of her private key are these 2 large primes. And then Alice will multiply P times Q to get a number n, and that number n is part of her public key. So she's going to tell everyone the number n. If I told you a number like 21, it's easy for you to factor it, to figure out 21 is 3 times 7. But if I told you a really big number, we believe it's hard to factor. There's no efficient way to recover the prime factorization. So Alice can tell everyone n, but other people have no way to know what p and q are. They can't figure out how to factorize n. Okay, the next step is that Alice is going to choose an exponent e. And e is kind of arbitrary. It might be a number like 3. For technical reasons, it has some constraints. It has to be relatively prime to p minus 1 times q minus 1. But you don't have to worry too much about those constraints. You can think of this as Alice just chooses an arbitrary number, like the number 3 maybe. And then Alice is going to compute the number d, which is the multiplicative inverse of e. It's like the 1 over e. It's like if you wanted to divide by e, it's the number you would multiply by. Okay. Modulo this number, p minus 1 times q minus 1. And in CS70, I think you saw extended Euclidean algorithm, which can be used to compute a modular inverse. So there's an efficient algorithm for that, which Alice can use to figure out the value of d. And then Alice's public key are n and e, and the private key are d, and maybe p and q. And given n and e, it's believed to be hard to recover, like to compute or guess or predict or infer what d would be. And then for encryption and decryption, we're going to use these numbers in the public key and the private key in a way I'm going to show you in just a moment. Yeah, I see you're waiting patiently.
Yeah, like Mark, why is it efficient to just pick random?
Haha, yeah. They're kind of sparse, but not too sparse. You might have to try 1,000 times, and then you'll probably find one, and 1,000 is not a big deal. But it's not like you'll have to try 1 billion times. Yeah, like these operations with numbers, multiplying and testing primality is so fast that we can do 1,000 of them, and you kind of won't even notice. It takes a second or something. Yeah. Sorry? You don't have to keep p and q. I conceptually, I think of them as being kept, but Alice could throw away p and q. Okay, so now with all that defining all these parameters, here's how encryption works and here's how decryption works. Encryption, to encrypt the message m, Alice raises it to the eth power and reduces modulo n. And there's an efficient algorithm to do that. You don't actually first raise to the eth power and get a giant number and then divide by n and take the remainder. Instead, you kind of reduce mod n at each intermediate step of the computation. And so that can be done efficiently. And decryption is to take the ciphertext and raise it to the power d mod n. So encryption and decryption are the same, except you just use a different exponent. And all this craziness about how E and D and N were chosen was carefully set up to make sure that decryption undoes encryption. D was carefully chosen so that when you decrypt in this way, an encrypted ciphertext, you'll get back the original message. Okay, so that's the RSA scheme. It might be kind of mysterious. So for those of you who love math, I can show you why does this work? Why does decryption undo encryption? I can show you the math of that. But if you don't love math, you can just skip that. I got a question. You could also pick D and then compute E as the modular inverse of D. Yes, that's correct. That's totally correct. Okay. So why does picking E and D in this way ensure that decryption undoes encryption? there's some number theory. And if you like number theory, I'll show you. And if you don't like number theory, you can just kind of zone out for 5 minutes. Two things from number theory, two facts from number theory that we're going to use in this argument. One is this Chinese remainder theorem business. So if I have two numbers that are equivalent modulo p, and they're also equivalent modulo q, then they're equivalent modulo p times q. Like if you and I are thinking of a number and we discover that we have our numbers have the same remainder mod 3, and our numbers have the same remainder mod 5, then our numbers have the same remainder mod 15. That's the Chinese remainder theorem. And then there's Fermat's little theorem, not his famous one, but the baby one, where he shows that if you take any number and you raise it to the p minus 1 power, the p minus 1 is a special exponent when you're working modulo p if p is a prime, because raise any number to the p minus power and you get back 1. Okay, so I'm not going to prove those two theorems. You just got to take those on faith. But given those two theorems, we can do some calculation about what happens if you encrypt a message M and then you decrypt that ciphertext. Okay, so encrypt a message M and you get M to the E. All of these numbers are going to be taken modulo p, so I'm just going to leave out the mod p in my verbal. When I say the ciphertext is M to the E, what I really mean is it's M to the E modulo p. So the ciphertext is M to the E, and then if we decrypt that ciphertext, we get M to the E to the D. So what we're trying to do is figure out what we get back when we decrypt the ciphertext. In other words, we're trying to figure out what the value of M to the E to the D is. M to the E times D power. What does that reduce to? And here, we're going to take advantage of how E and D were chosen. E and D were chosen so they're multiplicative inverses. Or another way to say that is if you multiply E times D, then you get back something that's 1. But not 1 mod P, not 1 mod N. It's 1 mod this funky thing. P minus 1 times Q minus 1. So in particular, ED minus 1 is a multiple of this funky thing, P minus 1 times Q minus 1. So ED minus 1 is a multiple of P minus 1. So this M to the ED I can write as M to the ED minus 1 times M to the 1. And M to the ED minus 1, we previously had something to say about ED minus 1. That's a multiple of P minus 1. So this is M to the P minus 1 times some constant. But what can I say about M to the P minus 1 power? Which of these theorems is helpful for telling me something about M to the P minus 1 power? Fermat's little theorem. Fermat's little theorem says when you're working modulo P, raise anything to the P minus 1 power, and what you get back is 1. So M to the P minus 1 is just 1. What's 1 to the Cth power? Where C is some constant that I'm not telling you. 1. 1 to the Cth power is 1. 1 to any power is 1. 1 times 1 times 1 times 1. It's 1. So M to the P minus 1 times C must also be 1. So that whole term drops away, and all I'm left with is the M term. So I did this long, convoluted, complicated calculation to discover that the result of decrypting the ciphertext is the same as the message M modulo P. And I could do the same reasoning modulo Q and discover that the result of decrypting is the same as the message M modulo Q. And so by the Chinese remainder theorem, it must be equivalent modulo P times Q, or in other words, modulo N. So decrypting gives me a number that is equivalent to the original message modulo N. All the numbers are reduced mod N, so they're between 0 and N minus 1. So if two things are equivalent, have the same value mod N, and they're both between 0 and N minus 1, they must be the same. So when I decrypt an encrypted value, what I get back is the same as what I started with. Uh-huh.
From the definition before, like looking more at this correctness, this is deterministic, right?
Yes, encryption is deterministic. There's no randomization or nonces or anything in there. Yeah. So we're gonna have to talk about that in just a minute. Good catch, yeah. All right, I'll put another proof in the slides that we're not gonna walk through, but there's another way to prove it. If you want, using something called Euler's theorem, which is a generalization of Fermat's little theorem. Whatever, same thing. So there's multiple ways to prove the correctness of RSA. So that's why RSA was designed the way it is, to choose E and D in this way. We know that it is correct in the sense that you're going to decrypt. Decryption will give you back the original message. Is it secure? The answer is we think so. We have no formal mathematical proof. We don't expect to find one. But as far as we know, the only way for an eavesdropper to try to infer what the message is from the ciphertext without knowing the secret key is to try to factor n, and it's believed that that takes basically exponential time. So it's believed that there's no way for an eavesdropper to figure out what the message was. But what I showed you just here is deterministic. So it can't possibly be secure in the sense of this in CPA game. So as your good instincts here, something is not right. Something's not right yet. And then what's not right is we need some randomization. And so to actually use this, there's some little subtle tricky bits that you gotta take care of. Same as with El Gamal also, that we need some randomness in there. And so in practice, what people do is they use what's called a padding scheme. It's different from padding for modes of operation, but they take your message, they append some 0 bits, they append some random bits that would play the role of like an IV or a nonce, and then they encrypt in this way. So if you're actually encrypting, don't like try to implement based on this description, because I've left out some details that are not conceptually that important, but that are important for security, including randomization. And then when you add those details in, this is now in CPA secure. And there's a standard way of doing this padding. It's called OAAP, which adds some randomness. And if you use that method, then it's in CPA secure. And if you're curious, you don't need to know how it works, but basically you take the message, you add some 0 bits, you add some randomness like an IV, you do some stuff to mix them all up, you do a reversible operation to combine them to get something, and then that something you get, you encrypt with RSA. And this can all be reversed. So the recipient undoes all these operations and checks that what they get back is some message looking thing followed by some zeros, followed by some, and it could be anything, the random IV part. Okay. So that is public key encryption with El Gamal and RSA. Two, both perfectly reasonable ways to do public key encryption. You use either one, whichever you prefer. Now in practice, public key encryption is slow. Not really slow, but not as fast as we would like. Like symmetric key encryption, I can encrypt a gigabyte per second or gigabytes per second with AES symmetric key encryption. With RSA or El Gamal, encrypting one message takes a millisecond, 10 milliseconds. So I can do 10 or 100 of them a second. So it's not super slow, but it's not super fast. And if I wanted to send a really long file, like a gigabyte of data, doing this like a billion times would be really, really slow. So the downside of the public key encryption is it'd be really slow if you had a lot of data to send. So we have a little trick to deal with that. It's called hybrid encryption. That combines the best of both worlds. The best of public key encryption, you don't have to have a shared key in advance. And the best of AES encryption, it's really fast. Does anyone have any ideas how we might do that? How might you combine those two to get the best of both worlds? How about we take a break, and when we come back, we look at how to combine these two. Let's take a 3-4 minute stretch break. Take a break. All right, let's get started again. So I got this gigabyte file to send you, but oh no, I didn't share a key with you. I could send it to you by RSA. That way I don't need a shared key, but it'd be kind of slow. AES would be awesome, but I don't have a shared key, so I can't use it, but it would be fast if I could. How do I send you my gigabyte file? Yeah. 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 If we had a shared AES key, we could just encrypt the file with AES. So pick an AES key and send that with RSA. And then encrypt the file with that key and send both of those to you. So when you get the RSA ciphertext, you can decrypt that and figure out the AES key. And then when you have the AES key, you can decrypt the AES encrypted file. All right, so that's called hybrid encryption. We generate a symmetric key K, sometimes called a session key, and encrypt it under the public key. And we use that to encrypt the data with symmetric key encryption. Okay, so this way, it's very efficient. I do one RSA operation on a short message and then an AES on a giant amount of data, almost as fast as AES. And it doesn't require any shared key, just like public key cryptography. Also, it addresses a limitation of RSA and El Gamal that they can only encrypt short messages because the message can't be any longer than P or N. Okay, so this is in practice what everybody does. If they want to do public key encryptions, they actually do hybrid encryption. All right, I think I'm going to stop there on public key encryption and transition now, but I want to take a break and see if people have questions or want to like get a sense of where we are overall. Yeah.
Is this a, like, is that difficult?
Huh. This is used for end-to-end encryption. Yep. If my web browser connects to my bank to do some online banking, my web browser encrypts something with the bank's public key. And end-to-end means that the encryption is between my web browser and the bank server. It's not like between my computer and my ISP, and then my ISP and some other router, and then that other router and my bank. It says that even though the encrypted message is passing through all these routers, they don't have any of the keys. They can't decrypt any of the traffic. So they are seeing only ciphertext. That's what end-to-end means. So if I'm using an end-to-end encryption, I have to trust my browser to keep secrets, and I have to trust the bank to keep secrets, but I don't have to trust my ISP. I don't have to trust the Berkeley Wi-Fi. I don't have to trust other people on the Wi-Fi network. I don't have to trust any of the routers. Uh-huh. How does the security of RSA compare to the security of AES? They're both awesome. Like, we have no idea how to break them. As far as we know, it would take an exponential amount of resources to break them, meaning like, way more than will ever be assembled in the lifetime of the solar system. Yeah, so they're both very, very, very secure as far as our current knowledge is. We don't lose anything by using RSA. It's slower, so we lose something in performance, but we don't lose in security. And to give you a sense of why that might feel reasonable, with El Gamal, we use this prime number P, and with RSA, we use 2 prime numbers. The bigger those prime numbers are, the more secure it is, like the harder it is to factor. So what we in practice do is we choose large enough prime numbers so that it's really, really, really hard to break. Like as hard to break as AES, breaking AES would be. The larger the prime number, the slower it is, but we just live with that because we're using hybrid encryption and it's not too slow. Yeah.
In more practice, like especially looking at that last point.
Yeah.
Is it just easier to just like use different techniques together to cover like each other's weaknesses almost?
That's kind of what we're doing. Yeah, covering each other's weaknesses.
Just trying
to make one whole system that's perfect. Yeah, each is kind of like team effort. They each are good at a different thing. Yeah. Okay, so I want to talk now about digital signatures. So encryption is about confidentiality. Digital signatures are about authenticity. When Bob receives an RSA encrypted message from Alice, he has no way to know it came from Alice. It could have come from anyone. Digital signatures provide a way for Bob to know who sent him a message, to verify the sender of a message. Okay, so digital signatures are going to be the analog of message authentication codes, but in the public key world instead of in the symmetric key world. Okay, so public key cryptography. So we're going to assume that everybody, each person has generated their own private key and has their own public key, and they publish the public key. And there's some way for me to figure out what your public key is that can't be tampered with, and some way for you to figure out what my public key is that can't be tampered with. So that's just kind of a base assumption we're going to make. And I'll tell you how we could like achieve this assumption later. But for now, just assume that there's a way that Alice can know what Bob's public key is and no one can mess with that. Public key signatures are an algorithm that enable Bob to verify who sent him a message. And the way that works is Alice has a private key and she can apply that to the message to get something like a MAC tag. And the MAC tag, anyone who has Alice's public key can verify that this MAC tag could only have been generated by Alice, could only have been generated using Alice's private key. So it's like a MAC, but anyone can verify. Only Alice can compute the MAC, but anyone can verify that the MAC is correct. It's kind of a weird kind of a MAC. Except instead of calling it a MAC, to highlight that this is public key cryptography or just because whatever, it got a different name, the name that's known as digital signature. Okay. So a digital signature has three algorithms or operations. One is a way to generate a public and private key pair. One is a way for Alice to sign a message with her private key. And then finally, there's a way for anyone given a message and that signature, that tag, for anyone to verify that it's correct. There's the correct like tag or checksum or signature on the message. Correct meaning could only have been applied by Alice. So the signing needs the secret key. The verifying doesn't need the secret key. Verifying is going to be possible with just a public key. The verify is like a way to check that it was correctly computed. And it's kind of interesting that we have a way to check that the secret key was correctly applied without needing to know the secret key to do that check. It's kind of funky. Okay. In practice, just as we use hybrid encryption, we're going to use some like hybrid thing with digital signatures too. We're going to make a digital signature scheme that works well for a short fixed length message. And then to deal with long messages or arbitrary length messages, what we're going to actually do is we're going to first hash the message, and then we're going to apply the digital signature to the hash of the message. And because the hash function is collision resistant, that is going to be as good as signing a long message, but is a lot more efficient. So how do we do signatures? There's multiple public key algorithms for computing a digital signature. One of them uses RSA. This can be a little confusing. It's not the same scheme as RSA encryption, even though the math looks really similar. It's super inspired by RSA encryption. But it's actually like a different algorithm because it does signatures. So for RSA encryption, encryption raised to the eth power, decryption raised to the dth power, and if you do both, you get back the original message. And actually this like operation go raised to the eth power and then raised to the dth power, you could do it in the other order too. If you took a message m and you raised it to the dth power and then you raise that to the eth power, you would get back m. Doesn't matter which order you do it. So signature, RSA digital signatures are going to like do the same operations but in the other order in some sense. The digital signing is going to involve raising to the dth power. D is the private key. And then the verifying is going to involve raising to the eth power. And verifying is going to give you back the original message m, and you can check that that matches what message you were expecting. Okay, so Key generation is the same as RSA encryption. We end up with a public key N and E, and there's a corresponding private key D. To sign a message M, we hash it, and then we raise the hash to the dth power modulo N. And the signature is that number. It's a number between 0 and N minus 1 that you get. Now, someone who knew the private key could check the correctness of the signature by just recomputing the hash and recomputing the dth power and checking. But we want this to be verifiable by someone who doesn't know the private key also. And so the way that that can be done is the recipient can take this alleged signature, raise it to the eth power, and check whether what that gives them is the same as the hash of M. If the signature was generated correctly, raising it to the eth power should undo raising it to the dth power, and they should get back the hash of M. So this verification process, if this equality holds, then the recipient accepts the signature as valid, concludes this message M must have been from Alice. I can accept it as authentic. And if the equality doesn't hold, then the recipient says, oh no, something's gone wrong. I better ignore this message entirely. Yes. Yeah, the signature is H of M to the dth power mod N. Yes, that's correct. You can think of this as signing the hash of the message, but you can think of it as just signing the message. What the signature does is compute a hash along the way. Okay, so that's RSA signatures, and the proof of correctness, why this works is the same for why RSA works, why RSA encryption works. Sometimes you will find people say, I want to inoculate you against this way of talking about it. Some people say that an RSA signature on a message M is encrypt with the private key, and then verification is decrypt with the public key. And I don't really like that personally, because I think signature is a different operation than encryption. It's kind of confusing to think about it as encryption, but maybe you can see the resemblance here. Still just raising to a power. There is also, there are other signature algorithms. There is an analogy of El-Gamal encryption, but for signatures. A signature scheme that is based off of Diffie-Hellman. And you don't need to know it. I'm not going to try to teach you it. It's a little bit convoluted, but there is one. It just so happens that it's been the source of a lot of implementation flaws, because part of that signature algorithm involves when Alice wants to sign something in the DSA scheme, she generates a random number, secret number, called K, and does some stuff depending on K on the message. And it turns out that if anyone comes to learn that secret value K, then they can like recover her private key and break the scheme. So she has to keep it secret. And also, if you assign two different things with the same value K, this K is like an initialization vector. And if you sign two things with the same K, then that also reveals the private key, which is really bad. And I just thought you might enjoy hearing about like some attacks on digital signature schemes. I said that these digital signature schemes are secure, and they are, as long as you implement them correctly. And if you look at the history of how people have, when there have been successful attacks against digital signature schemes, essentially all of them were not attacking the math, but they were making use of some implementation bug that they weren't implemented correctly. And in the case of DSA, one turns out to be really common implementation bug is not generating this value K randomly. For instance, at one point, the Sony PlayStation 3, it was discovered that you could hack it and like load arbitrary code on there because, oops, well, they signed firmware, would only let you load firmware that was signed by Sony, But oops, they reused the same key for multiple signatures and it was possible to recover the private key and then sign your own firmware. Just an implementation bug. They're using a perfectly secure algorithm, but their implementation had this mistake in it.
I haven't. Like someone can just check about the PS2 all of it.
Yeah. When something like that happens, what does Sony do to recover? They can change their private key, but it's not that easy because they can change their private key and change the public key in all the new PlayStations that they sell. But all the old PlayStations still have the old public key and are expecting a signature under the old private key and won't accept a signature under the new private key. So what do you can provide stronger security for the new PlayStations that you sell, but the old ones are hacked. Unless you can upgrade that software to upgrade to use the new public key, then maybe you can upgrade the old ones and secure them. And like this mistake just keeps happening again and again. There were some Bitcoin wallets that made this mistake and you could like steal Bitcoin, and it was a bug in a like little hardware authentication token. And so when you're implementing crypto, there's a bunch of these little nitpicky implementation details that can turn a super secure algorithm into one that's completely broken if you're not careful. And basically the best advice is to choose a good library that implements this and takes care of all these nitpicky details for you. And in project 2, we're going to try to give you an API that implements a bunch of this stuff for you. So you don't have to like know how to apply OAP padding or stuff like that. So summarizing, public key encryption. Public key cryptography gives us a way to both provide confidentiality with encryption and provide integrity with digital signatures. Involves this public and private key pair. And a key requirement is I need to have some way to get your public key. If I can get your public key, then we can communicate securely. The good news is your public key doesn't need to be secret. So I can write it on my office door, I can put it on my business card, I can hand it out to everyone. There's nothing secret in the public key. Why would I ever use a Mac when I have a digital signature? Why wouldn't I just replace a Mac with a digital signature everywhere? Never use a Mac again. Digital signatures are just better. What are you thinking?
Be able to sign it. It's not a city. Because you, well, like, say, okay, well, I will want to set it back from like some arbitrary number. I can't use, like, that would require certain items.
Oh, yeah, okay. I have a joint bank account with another person. Payments are allowed to come from either of us. So maybe you could use a message authentication code with a key that's known to both of us. And the recipient doesn't need to know which of us applied the MAC tag. Either one of us can apply the MAC tag and it'll be valid. Okay, potentially a benefit of MACs. You could also do that with digital signatures too, you'd have to have some notation somewhere that says a digital signature from Dave or from Dave's friend, either one of those is allowed to spend money on this account. So both would be two valid ways to implement like a joint bank account. Maybe you could argue a Mac might be a little bit conceptually simpler. What are you thinking?
Could two people have the same digital signature?
Could two people could have the same private key? That's a good point. Oh yeah. Okay, if we want to do a joint bank account, instead of using a Mac, we could use a digital signature and I share the private key is known to both me and the other account holder. Good point. Okay, so maybe that's not a real advantage of a message authentication code. So just digital signatures for everything and get rid of message authentication codes? I wasted your time by teaching them to you? Yeah? Nice, nice. You said two things, but the first one was the one that in practice is the big deal. Turns out that Macs are faster than digital signatures. Symmetric key encryption and message authentication codes are really, really fast. Public key cryptography is ish. I'd rather really fast over ish. So that's the primary reason why people use message authentication codes, is if they need really fast. But if you didn't care about that, apart from that, for most purposes, digital signatures would just be better. Yeah. Good question. Yeah.
For signatures, when everyone needs to agree on one hash,
Everybody has to agree on one hash function.
what's that?
When we agree on like, we're going to use RSA signatures, we typically also agree on what hash we're going to use.
Oh,
So I might tell you, by the way, I'm using RSA OAP with SHA-256 hash.
and you can give that up.
And that's public, and there's nothing secret about that, yeah. Yep. Yeah, what do I mean by really fast? You can encrypt, compute a message authentication code, compute hash functions at a speed that will let you process, I don't know, a gigabyte a second, gigabytes per second. And you can do public key operations, RSA, Elgamal, RSA signatures, DSA signatures. Those you can do 100 of those a second, 1,000 of those a second. And each one handles some fixed length data. I don't know, 20, 40 bytes, something like that.
Is that like the fact that you hash the message?
Including that you hash them. Well, if the message is really long, you add on the time to hash the message. Your message has to be really long to take more than, a few milliseconds to hash. But if your message is really long, yeah, then add on the time to hash it. Okay, this is a great time. Let's take a break. Let's take a 5-minute break. Let's have some snacks. Let's kind of relax and chill out, and we'll reconvene in 5 or 6 minutes. okay, I suppose we can be responsible and like get started again and do stuff. We've been spending a lot of time on cryptography, so I want to show you a few last things and start to wind down on cryptography so we can start some new topics. What I want to show you today for the rest of this lecture is primarily this business of how do I get someone else's public key? And that's what the certificates is going to be about. And then I'll just show you a few random like odds and ends and like uses of cryptography and stuff. So we've just been talking about public key cryptography. And one of the key requirements for public key cryptography, if I want to send a message to Bob, encrypted to Bob, I need to know Bob's public key. And if I want to verify a signature that Alice applied to a message, I need to know Alice's public key. So I need a way to get people's public key. And the key requirement is that I know their public key in a way that it couldn't have been tampered with. So like Alice and Bob could put their public key on their webpage. But I need a way to make sure that like Mallory hasn't modified the web page that was sent to, otherwise I'd be in trouble because I would be getting not their actual public key. So certificates are going to deal with that challenge. Yeah.
This is the, like, aliens under security, right? Like, we don't really, at this point, our scheme should be unbreakable, but it's just like, okay, there is something true correctly, I can actually set.
It's we're at a point now where if there's an eavesdropper present, but there's no Mallory tampering with messages, we solved everything we care about. We have a way to do confidentiality with public key encryption. We have a way to do integrity with digital signatures. But the scary bit is if there's someone, a Mallory, who's modifying tampering with messages. When I go to look up Bob's public key, I might not get back Bob's public key. I might get back something else entirely. I might get back Mallory's public key. She claims it's Bob's, but it's actually not Bob's.
Mallory would be able to do.
And then Mallory can decrypt this message that I sent. I sent it. I wanted only Bob to be able to receive it, but Mallory can decrypt it. Yeah. So that's the lingering problem that we're going to try to look at how we deal with in practice. And the way we deal with that is something called certificates. And the catch is just what I've been explaining, that it's not secure. The schemes we've described to you so far are not secure against someone who's actively modifying and replacing messages. In particular, it's not secure against a man-in-the-middle attack. So let's say Alice wants to send a message to Bob. Alice needs to know Bob's public key to do that. So the first thing Alice does is ask Bob for his public key, and Bob sends it to Alice. And then Alice can encrypt her message with Bob's public key. The problem is that Mallory can get in there and replace that message from Bob, tamper with it, modify its contents. So instead of it containing Bob's public key, it contains Mallory's public key. And then Alice will encrypt under whatever public key she receives. So she'll be encrypting under Mallory's public key. And now Mallory can decrypt. Mallory can secret message that she wasn't supposed to know. So pictorially, it looks kind of like this. Bob sent his public key, but then Mallory modified that to a different public key. Alice took whatever public key was sent and encrypted her message under that, but she has no way of knowing whether that public key she received is Bob's or is someone else's. All right, that's the problem. That's the problem statement. The certificates are designed to solve. So the natural idea for how to deal with this, if we're worried about someone tampering with, modifying a message, how do we protect its integrity? How do we verify the authenticity of a message? We have two schemes for doing that: message authentication codes and digital signatures. like kind of digital signatures are better in every way, so let's just try digital signatures. The obvious thing to do would be to say, oh, let's stop this man in the middle attack by signing Bob's message. When Bob sends his public key, let's sign that. So Alice can verify that it hasn't been modified. Yeah, kind of like a very intuitive thing to try. But there's a problem. If it's Bob who's doing the signing, then to verify, for Alice to verify the signature, Alice needs to know Bob's public key. But that's just what she was trying to figure out in the first place. She doesn't know Bob's public key, so she's asking Bob what it is. She gets back some signed message from Bob. Now to verify that she needs to know Bob's public key. Wait, she started with one problem and ended with the same problem. It's like the joke about how the computer scientist died in the shower. You know, she was washing her hair and the instructions on the shampoo said rinse, lather, repeat. You end up with a chicken and egg problem. If you don't know Bob's public key, you can't verify a signature from him. So you can't verify this message from him wasn't modified. So the problem is that if you start from nothing, if you start knowing nothing, you're trusting no one, you're host. You can't create something out of nothing. And the solution is don't start from nothing, start from something. We're going to need to start with some entity who we have a relationship with and we trust. And then they're going to be able to introduce us to others. So that might sometimes called a trust anchor. It's someone that we trust completely and who can help us figure out stuff like what Bob's public key is. Okay, so it'd be like that really well-connected friend of yours who knows everybody. You want to meet someone you don't know, you like get in touch with them. Hey, can you make me an introduction? That's the role the trust anchor plays. So a certificate is like an attempt to make this signing idea, but we're going to make it actually work. We're going to stick with this idea of signing the message from Bob, signing the message that says what Bob's public key is. That was a good idea. The bad part was that we're going to having Bob sign it doesn't work. It has to be signed by someone whose public key we already know. That's where the trust anchor comes in. Okay? We're going to have it signed by someone who we know and whose public key we know. Okay, so a certificate is a signed statement about, like the statement is X's public key is Y. The statement is about what the public key of a particular person is. And it's going to be signed. So there's the person whose like public key the statement is talking about, and then there's the signer of this endorsement. And there's going to be two different people. So the signed statement is going to contain the identity of the person, like Bob, and it's going to contain Bob's public key. And to like show you how certificates work, I'm going to like use some notation. So let me just set up some notation to write digital signatures in a short, more concise way. I'm going to put some like little curly brackets. And then after the curly brackets, a subscript. And the subscript is the key that this is encrypted or signed with. You're going to have to figure out from context whether that's an encryption or a signature. The stuff inside the curly brackets is the message that is being signed or encrypted. The subscript is the key. So if it's a public key, then you can infer that it's encryption with that public key. And if that subscript is a private key, then you can infer that it is a digital signature with that private key on that message. So a certificate now is something like the bottom line here. You see this, Bob's public key is PKB. That whole thing signed with SKE. That's a certificate. So it's a signed statement. In this case, it's signed by Evanbot, signed by Evanbot's private key. It's a signed statement, and what the statement says is the statement tells us what the public key of some person is. So it contains an identity, Bob, and it contains the public key, PKB. That's called a certificate. And if we all trust Evan-bot implicitly and absolutely, Evan-bot is completely trustworthy, Evan-bot knows everyone, Evan-bot knows everyone's public key, then we can, and if we know Evan-bot's public key, then we can verify the signature. So we can verify that this message really was endorsed by Evan-bot, because no one else knows Evan-bot's private key, and we can verify that signature. And then because we trust Evan-bot implicitly, therefore we can believe that what Evan-bot tells us is true. So when we receive the certificate, we can verify the signature, know it comes from Evan-bot, and then therefore conclude that we now know what Bob's public key is, if we had this full trust in Evan-bot. So that's the idea. If there's someone we trust a whole lot, and they know what everyone's public key is, they can tell us. And the way they can tell us is by sending us a signed statement, a certificate. Yep.
I guess that's-
It's just a notation. It's the signature, digital signature.
Yeah,
Oh, this is some weird historical thing. The -1 is to like help you know that's a secret key, not a public key. I don't know. It's a lame notation. I don't like it. One semester I tried like using my own notation that I thought was more intuitive, but then it doesn't match what you'll find in any textbook anywhere, and that's confusing in its own right. So, sorry. So here's a way to think about certificates or how certificates might have been invented. Suppose Alice trusts Evan-bot and Alice wants to know Bob's key. Alice could send Evan-bot a message. Hey, do you know Bob's public key? Can you tell me what is Bob's public key? And then Evan-bot could respond. Bob's public key is such and such. And to make sure that these messages can't be tampered, they could be signed. It's really only the message from Evan-bot that's very critical, so that one's the one that needs to be signed. Who should sign that? Well, it's coming from Evan-bot, so Evan-bot should sign it. So you end up with a communication that involves Evan-bot sending a signed message to Alice that is of this form we've been talking about. It's an assertion about the public key of some particular individual, and it's signed and endorsed by Evan-bot. Now, here's the end-to-end digital signature part. This signed message is just a bunch of bits. It was transmitted to us over the internet. Once we receive that bunch of bits, we can verify the validity of the signature, and we don't have to worry about who sent it to us or where it came from or like what routers it came through. We don't have to trust the routers that it came through. We don't have to worry if somebody's tampering with my Wi-Fi network. Once I have those bits, it's sort of self-verifying, like contains all the information needed for me to verify that it's correctness without regard to who gave it to me. So I actually don't have to get that from Evan-bot. I could have gotten that from anyone. Like Evan-bot could have told Charlie, and Charlie could have told Doug, and then Doug could have sent that message to me. And that would also be just as good, because I can still verify the signature and I still trust Evan-bot. So I don't actually have to care how that message gets its way to me. Just as soon as I've got it, I'm good. So for instance, Evan-bot could anticipate that Evan-bot might get asked this question and pre-generate the response and start sharing that with everyone, posting it publicly. Or Evan-bot could give it to Bob, and Bob could give it to Alice. Bob could say, hey, I bet you're going to want to send a message to me. Here's my public key, and here's how to verify it's correct. Here's the statement from Evan-bot that you can use to verify it's correct. Alice can get it from anyone because it's like a self-authenticating statement. So that statement is a digital certificate, and it doesn't have to be transmitted in an interactive conversation between Alice and Evanbot. It can be like pre-computed and cached and handed, stored, stored by Bob and provided to Alice, just when she needs to know it.
Be very, but sure that whatever public key
We have to be really sure that we know what Evanbot's public key is because we're putting a lot of trust in Evanbot. How do you do that? The real world answer, for instance, in my web browser, is that my web browser has hard coded into the binary the Firefox or the Chrome public key, or the public key of the Evanbot, the entity who's trusted. Or my operating system, when I install my operating system, it has hard coded in the public key of, I use Fedora. So it has the public key of the Fedora Linux maintainers. And whenever I want to do a software update, they're all signed with that private key, and I can verify the validity using that public key. It's hard coded in the stuff that's initially installed. How do I know that was correct? I don't know. Might have a good answer, might not. If I got a CD in the mail, maybe I can trust who I got it from. But if I downloaded it over the internet, I don't know. Maybe I shouldn't trust it. Except maybe I can, because if I downloaded it over the internet, maybe I downloaded it over HTTPS on another computer. And so that other computer was using public key cryptography to verify it using the HTTPS. So how did that computer know it had something hard coded that? So it's kind of like the walking back, this long, long chain. I knew because that computer knew, because that knew, because that person knew, because, and you hope that nobody ever made a mistake anywhere there along the line. Yep.
this, that Evanbot sent to Alice.
Yeah.
to use, Evanbot's public verify that this signature was by not or
That's right. This is a digital signature. There's no encryption here. There's no encryption needed because there's nothing confidential. It's all public information. So all that's happening is a verifying a digitally signed statement.
how do we know that this was signed by Evanbot?
How do we know this was signed by Evanbot? I have to know Evanbot's public key, and then I have to verify the correctness of the signature with the RSA verification procedure. Okay, so using this idea, one design is you could think of as like a trusted directory. That there is one trusted directory, there's one service out there, one entity that is responsible for knowing everyone's public keys. When I generate a public-private key pair, I go tell that trusted directory my public key, and they authenticate me somehow. Maybe they look at my driver's license. I don't know how. Maybe they look at my student ID. And that entity keeps a giant database of everybody's name and their public key. And if I want to know your public key, I go ask that entity to help tell me what your public key is. And they look it up in their database and they send me a signed statement. And I don't actually have to ask them. It could be that when you registered your public key with this trusted directory, they generated a certificate proactively, gave you that certificate, that bit string, and now you can give it to me if I want to communicate with you. So I don't need to ask the trusted directory. I get it from you. I get the certificate from you. You got it from the trusted directory. Kind of sort of in the trusted directory, but this way I get it from you. I don't have to make a network connection to this trusted directory. This is like a performance optimization. The trusted directory doesn't have to get all these queries all these time. Every time anybody ever wants to send any email ever, no, I don't need to contact the trusted directory. I just need to get their certificate from the recipient. If the assumptions are all valid, this is a secure way to exchange public keys. What do you think might be some of the challenges or limitations or I don't know, issues or tricky bits in doing this in practice? Yeah?
Still have like cache.
Okay, that's one problem. Yep, if Bob's computer gets hacked, the hackers get their copy of Bob's private key, it's been compromised. This trusted directory will still have the old public key. There'll still be the certificates for the old public key. So it may be hard to recover from compromise. Absolutely. And I have a slide on that. Maybe a single central directory doesn't scale so well. There's like, how many people use the internet? I don't know, 3-4 billion people. So that's a giant database. And storing the database isn't that big a deal, but what part would be harder for them? Communication would be hard because everybody is communicating with this trusted directory a lot. Though even that part you can optimize and make pretty efficient because of the certificate business. If I want to communicate with you, I don't have to contact the trusted directory. I just ask you for the certificate that you got from the trusted directory. So most of the time, the trusted directory doesn't have to be part of things. But what else might be painful? Yeah? What if you run out of certificates? Do you want to say more about how you imagine that might happen, or? We basically can't run out of certificates because a certificate is like a bit string. It's like a message. You can put any message you want, and you can sign any message you want. So there's kind of no limit to how many messages you could have. Can we hit the upper limit of how many unique bit strings there are? Well, it's unlimited length, or you're not likely to run out. Yeah, so I don't think it's going to be an issue. Yeah?
We have the same.
Enrollment, the same issue as before when enrollment happens. How does Bob? Yeah. I kind of hand waved my part over that because that could be challenging. Like if the trusted directory personally knows Bob, okay, fine. Then they can verify that's Bob. But if you want to scale, then it's going to go beyond personal relationships. So how does some company authenticate some person on the other side of the country or on this other side of the world? Do they I don't know, send an email and attach your photo ID as an attachment to the email, but wait, can I just send a fake email and use someone else's photo ID or fake up the photo ID? Or it's kind of challenging to figure out how to authenticate the individual during enrollment time. Yeah, that's pretty painful. So there's a big scaling issue there. Anything else? Yeah?
Making central record every computer, phone, operating system, browsers, just not really feasible. We have to manufacturers that all work together.
We'd have to get everybody to agree on who this trusted directory is. Any thoughts on why it might be hard to get everyone to agree on who to choose as the trusted directory? Yeah, I agree with you. That's pretty hard. Yeah? Everybody across all the country trusts. Yeah, it's kind of like trust is has to do with relationships. And not just the country, we want this worldwide. Yeah. Should this trusted directory be an American company? But then are Chinese companies going to trust it? Should it be a Chinese company, but then are American companies going to trust it? How do you pick one entity who everyone trusts? Maybe there is no one who everyone trusts. I'm not sure we're in a world where there's anyone who everyone trusts. So that's a big problem. We have to have total trust in this trusted entity, and everyone has to agree on one person who everyone has total trust in. That doesn't sound realistic. One more problem, you mentioned compromises. You want to say anything more about the risk of compromise? We talked about the compromise of Bob's computer. Any other kind of compromise risk we should think about? Yeah. If the directory gets compromised, what happens then? They could start issuing false certificates for everyone. So like all security of all your public key cryptography becomes broken if this one entity gets compromised. So it's all your eggs in one basket. And boy, that basket had better be really secure, or otherwise it's really bad. Yeah. So for those kinds of reasons, in practice, there's a lot of reluctance to use a single trusted directory. In the context of the University of California, maybe it's a little bit more feasible. Maybe you could deploy something like this if it didn't have to be the entire world, but it was just students and faculty and staff at the University of California. Maybe we could make this work. We have the president of UC be responsible for the trusted directory. If you want to know my public key, ask the president of UC. If you want to know Raluca's public key, ask the president of the UC. Sort of more plausible, because like in theory, maybe the president of UC is responsible for all hiring and all admission, and so could potentially know for who everyone is and who's maybe learn their public keys at hiring time or when you show up for freshman orientation. But I'm not sure it's really realistic, because the president of UC has better things to do than this. So it's kind of asking a lot of the president of UC to do this. But it's a little closer in the context of one organization. It's sort of closer to being imaginable because, I don't know, it's more local, or we have more relationships. I have more of a relationship with the president of UC than some random company. What people do in practice is they do this, kind of take this idea, but keep applying it down to very small organizations. The smaller the organization, the easier it is to build a trusted directory for that organization, but also the less useful it is because it's only useful within that organization. So what we actually have is we have some recursive hierarchy of organizations, like a tree structure. This is what people typically do in practice. For instance, we might have the president of UC doesn't know all of the faculty in UC, just knows who the chancellors of the 9 campuses are. That's pretty reasonable, I think, and knows their public keys. The president of UC knows who the chancellor of Berkeley's is and what their public key is. And maybe the chancellor of Berkeley knows all of the department chairs. And maybe each department chair know all the faculty in their department, or maybe all the head TAs in their department. And maybe each head TA knows all the TAs in the course staff organization, and so on and so forth. So this is kind of like a hierarchical nested structure here. And then we can arrange certificates that respect this organizational structure. So the president of UC signs a certificate for Rich Lyons' public key. Says Rich Lyons' public key, such and such. It also says, and by the way, also I'm delegating trust to Rich Lyons. Rich Lyons can endorse statements about the public key of any department chair. Berkeley. Rich Lyons, don't trust Rich Lyons to make statements about Irvine, but Rich Lyons can make statements about Berkeley. And then Rich Lyons can issue certificates for all the department chairs. And those certificates for the department chairs can say like Jelani Nelson's public key is such and such. And he is the department chair for the ECS department. And I'm delegating authority to allow him to sign any certificates for anybody in the ECS department. So if you see a certificate signed by Jelani Nelson for someone in the ECS department, then I hereby approve you to believe in that. And then Jelani Nelson could be the one who issues and signs my certificate that says my name and my public key and says I'm in the ECS department. But Jelani Nelson would not be like authorized to sign certificates for people in the political science department because he doesn't necessarily know the people in the political science department. All right, so this is like a tree of trusted directories or a tree of certificate authorities. And the root of that tree is the president of the UC. They're the root certificate authority. You have to have complete trust in them, but they don't have to know everyone. So they don't have to handle enrollment for everyone. They just have to know enough people they can delegate to. They delegate to these intermediate certificate, someone who signs a certificate. So this is kind of the kind of somewhat more realistic way we implement a trusted directory in practice. And on the web, when you want to connect to a website like Amazon, and you want to set up a secure connection to Amazon, if you use HTTPS Amazon.com, your web browser uses public key cryptography to encrypt and digitally sign the communications with Amazon. So your browser needs to know Amazon's public key. How does it obtain it? There is a certificate. There is a certificate that says Amazon, the public key for Amazon.com is such and such, signed by a certificate authority. And your browser has a list of entities out there that are trusted to issue these certificates. And it has the public keys of all those entities. Those are called certificate authorities, root certificate authorities. And today, most browsers have a list, not just one of those, but like maybe 100 of those. And it's an important thing, important part of what Mozilla and Chrome and Safari, what their team do, is they go out and they vet each of these entities, these root certificate authorities, to like audit their processes and make sure that they're carefully checking the identity of people before issuing a certificate and following good security practices and making sure to protect themselves so they don't get hacked and so on and so forth. So they have processes and teams whose job it is to audit them and do that kind of like checking. So we don't have to. They do it on our behalf. And a very nice thing is that creating the certificate is a one-time task that is done by the certificate authority. Sign the statement once when the person enrolls or the website enrolls. And then it can be cached and copied and passed around to anyone who needs it. So typically, when Amazon registers their public key with a certificate authority, the certificate authority signs it, gives them the signed certificate, and then when your browser connects to Amazon.com, Amazon responds by sending the certificate. Says, I know you might need to know what my public key is, so here's my public key and here's the certificate you can use to verify it so you know for sure that you're getting the right public key. So your browser doesn't need to contact the root certificate authority. Amazon is taking care of that for us. All right, so this is how we verify people's public keys and how things work on the web. Now there's some problems. This is kind of like our best effort, but it's not perfect by any means. One of the problems is revocation. What happens if some certificate authority messes up and they issue a bad certificate? Like, for instance, one of the certificate authorities famously issued a certificate for what Microsoft's public key is, but they screwed up. It wasn't actually Microsoft's public key. It was some random person on the internet who contacted them and claimed to be Microsoft, but they weren't actually Microsoft. That was really bad because then they could send software updates and code to anyone running Microsoft Windows and it would be accepted. So that was not good. So what do we do if that happens, if someone makes a mistake? Yeah, what do we do? There's this bad certificate that's signed by the certificate authority, VeriSign. It's now floating around out there. Everybody's browser trusts VeriSign, so they'll accept this certificate. They trust VeriSign. Now we want to recover from that. Let other certificate authorities.
Just check with other certificate authorities.
My browser could check with 2 or 3 certificate authorities instead of just 1. So if one makes a mistake, I have protection. Absolutely, we could. People don't do that in practice, but we could. That'd be a reasonable solution. Yep. Yeah, we could have an expiration date. So at least the impact will be mitigated. It won't be forever. At some point, it's going to expire. And we do. Certificates all have an expiration date. Bad news is that a lot of certificates are issued with the expiration date. They're valid for about a year. So after a year, this bad information will no longer be relevant. But for a year, this random guy on the internet can send anyone malicious code and have it be accepted. That's not so great. So, but we could set a shorter expiration date. We could make certificates valid for only 1 day or something. And then if VeriSign realizes they screwed up, stop issuing that certificate, and by tomorrow, things will be okay again. Yeah, I like that. Expiration dates, very good solution. Yeah?
Can you tell people who gave this certificate to that it's bad?
Maybe VeriSign could tell anyone they gave the certificate to is bad, don't trust this. Yes, but also no. There's a little bit of a tricky bit here. So VeriSign tells this random dude on the internet, we shouldn't have given you that certificate. Don't trust it and don't give it to anyone else. Is everyone else on the internet, everyone on the internet now safe again? What's wrong?
That guy can choose whether or not to tell people or not.
Yeah, that guy could choose to be like, yeah, whatever, I'm still using the certificate. Sucks to be you, VeriSign. Yeah, I mean, that guy may be malicious. Yeah.
I was gonna say, could you tell everybody else?
Oh, okay, tell everybody. That's a good, okay, good. Yes. Okay, so don't just tell the one person who the certificate was issued to. Tell everyone on the internet, this was bad, cancel it.
Is that viable?
Is that viable? So then we would have to figure out how to do that. How do we send this like public broadcast message to everyone on the internet? If you ever see this certificate, it's bad, don't do that. And that is a thing. That is a thing. It's called a certificate revocation list. And some browsers use this for a while. Like periodically, they would go to a master site and download the latest copy of the list of all the revoked certificates. So it wasn't a broadcast message sent to everyone, but browsers would check like once a day. Do you have any new ones that have been revoked? And that's feasible. It's kind of expensive because if you make mistakes, you might start to have a kind of a long list, and then every browser in the world is downloading a copy of that list. And so I guess maybe that's incentive not to make mistakes, but browsers didn't really like it. Browser vendors didn't really like it because it's a bunch of like downloads that every one of the browsers is going to have to do. It's an extra download and an extra network connection every day. It's not ideal, but it's doable. Yeah. Yeah? No? Yeah, I like your ideas. Basically, it's kind of not even fair of me to ask you this because like, what do we do if this happens? We're kind of like screwed. There's like no really good answers. There's just like ways to try to deal with it, like sort of, kind of as best we can. And none of the answers are really satisfying. And your answers are great. One approach is have an expiration date. Limits the risk, doesn't eliminate it, but limits the harm. And I think that's the trend where people are heading these days. They've tried the other things and they've discovered, oh, there's a lot of downsides of these other approaches. So I think this is the trend, is that we're heading towards certificates that are issued with a fairly short expiration date, and then you have to go ask for new ones frequently. But another approach is to periodically release a list of the bad certificates and everybody downloads a copy of that. Possible, totally possible. One of the really annoying things, one of the reasons why browser vendors don't like that and have moved away from that is you get into this between a rock and a hard place situation. What if your browser goes to download that list and can't reach the certificate authority to get the latest list of revoked certificates? Just not getting a response. It's not reachable. What should the browser do? One possibility is the browser could just keep going with yesterday's list, which is reasonable, like you use the best information you got available. Well, the problem is that could be a security vulnerability, because if someone gets a bad certificate, they could then mount a denial of service attack against the certificate authority so that the certificate authority can no longer respond and no one can get this updated list. So it might actually be insecure to continue with yesterday's list. Someone might be preventing you from seeing the latest revoked certificates. On the other hand, the safe thing to do would be to say, if I can't get a response to what today's list is, then I'll just assume that something really bad is going on and I won't trust any certificate. I won't make any communications, but then I can't get any work done today. So that really sucks too. So browser vendors kind of looked at this like two options and neither one sounded very satisfying. Why am I bothering adding this complexity if it's not giving me a whole lot of security? Okay, but that's basically how the web works, using certificates. In the early days, I've described this as a tree. Of course, we know in computer science, we love to generalize. If you can support 2 or 3, how about supporting an arbitrary number? If you can support a tree, how about a DAG or a graph? And in the early days, that was what people proposed. They proposed an arbitrary graph where anyone can issue a certificate for anyone else. So I would issue a certificate for all my friends, and maybe my coworkers, and then if I needed someone's certificate, sure, I could go to their department chair, but I could also try to go to their friends. Maybe there's any number of places where I could get a certificate for them. It was a really cool vision. Really nice idea. And maybe I could have greater trust because I could be getting a certificate from someone I know personally and I trust. But it introduced a ton of complexity. The original like secure email, the idea they had was, I'm gonna like set up these, I can't believe it. Oh my gosh, this is made by such geeky people. They said, this is the way you're gonna use your secure email is you're gonna generate a private key, and then you're gonna have a key signing party, a party where we all get together at a coffee shop and we all bring our public keys and we exchange our public keys and we issue certificates for each other. And that way, if I want to communicate with someone who I don't have their public key, but maybe they're a friend of a friend, and then my friend is issued a certificate from that key signing party. Kind of funny to imagine that this would be such a central part, that the people who designed this thought this would be such an important part of people's lives that they would go out of their way to like go attend a party to like sign certificates. Oh my gosh, can't think of anything possibly more exciting to do with my life. Totally didn't work. Right? Nobody's gonna do that. I've never been to a key signing party in my life. I've not signed a certificate for a single other person. And I am like one of the more, geeky, security intense people around. And if I'm not doing that, like no one's gonna do it. So what happened in practice is no one did that. No one did that. Come on. Instead, what happened was MIT set up this key server and where anyone could upload their keys. And they didn't have to know you. And they would just like add it to the list. And got their certificates from this MIT key server that did no verification whatsoever. Because it was completely unrealistic to like have a friend who I like trust and who has been to a key signing party with someone who's been to a key signing party with someone who knows that person I want to communicate with. Come on. So the model, the vision they had would have been like very secure as a beautiful vision, but it was completely unrealistic. And what happened in practice, because it was so unrealistic, was that people used it in a way that was like completely defeated all the security benefits. There was no verification happening. So instead, what we have today on the web is an attempt to get something. We're reliant on these like root certificate authorities to like be conscientious in checking who they issue certificates to. And I don't know who they are, so I don't know if they're doing a good job. It's a little hokey. I don't know. The security is like a little dodgy. I don't know how much I really should trust this, but it's better than this MIT key server that did no checking. All right, so this is the idea of certificates. Widely used on the web, a little dodgy, definitely has some weaknesses, but it's not bad. It's a whole lot better than nothing. And if you trust the certificate authorities, it now gives us a solution to this problem that we wanted. I don't have to share a key with you in advance. I don't have to have your public key in advance. I can obtain your public key from a certificate authority or from you if it's signed by the certificate authority. And I can have secure communications with you, confidential, digitally signed in a way that'll be secure, even if there's an eavesdropper and even if there's a man in the middle, even if there's an active attacker who's modifying messages. Because the signature on the certificate lets me verify that I really have your right public key, and then the public key encryption and digital signature make sure that Mallory can't tamper with any messages or learn any message. So that's kind of the end of the journey that we've been building up towards. This is kind of all the tools needed to do secure communication online, and this is the basis behind a lot of cryptographic systems that you'll use today. So I think I'm going to declare victory here. I was going to show you a few other random case studies. Any questions about this line of development here before I start a new topic? Yep. Discrepancy between two different root CAs.
It's like, maybe they say like Bob's public key is X and then the other one says like Bob's public key is Y or something like that.
Oh, what do we do if there's two root certificate authorities? One says Bob's public key is X, one says Bob's public key is Y. In practice, that doesn't happen. If that happens, one of them is wrong. One of them is lying, or one of them has been like not very careful about certificates they issued. And what happens if one of our certificate authorities is wrong or lying or not very careful? We're hosed. We might be hosed. So that's a bad situation. You don't want to have that happen, and you might lose security if that happens. And like, it's the certificate authority's job to make sure they don't issue bogus certificates. So software doesn't check for that case. Software doesn't look up Bob's identity with multiple certificate authorities. It just takes a certificate authority from anyone. Your web browser will take a certificate from any of those 100 certificate authorities. Doesn't care who. It doesn't try to check multiple of them. So your software, if that happened, your web browser wouldn't even know it happened. Like if there were one certificate authority issued one certificate for Amazon and another one issued a different certificate with a different public key for Amazon, my browser might not even know. When my browser connects to Amazon, Amazon would send back the certificate. If I'm contacting the real Amazon, hopefully they're sending me a good certificate. If there's malware present, malware might be modifying, tampering with messages, and might be sending me the bad certificate. My browser is going to get one of those certificates. If it's signed and by a trusted root CA, my browser trusts it. So my browser might be trusting something that's wrong, or might not be. Yeah. So if that such scenario happens where a certificate authority issues a bad certificate, we might be hosed. My browser might be sending data to an attacker instead of to Amazon. We just have to hope that doesn't happen. Don't have a really good answer against that, basically. There's a little bit of an answer. If you're interested, after class, we could talk about certificate transparency, which is a mechanism that was tried tended to can't prevent that, to maybe detect it. But the basic design has no defense against that. And it's happened. It's happened that hackers have successfully hacked into a certificate authority, exploited some vulnerability on their machines, taken control of their machines, and started signing certificates with bogus information. So it's definitely happened, and it could happen again.
They empowered themselves and said, we're gonna be the ones who are offering certificates now, or was there a collective group of people who said, these will be the certificate authorities? And then, like, not saying that they themselves have like their own like authority over them, they were just like, these will be the certificate authorities. Like, is the group of certificate authorities that we'll trust, or is it more like you can say, I'm a certificate authority, and the more people that you give certificates to is almost like a factor how good of a certificate authority?
In the early days, it was some of both. But the way things have developed now is that it basically comes down to what web browser vendors are willing to add in their list. Chrome maintains a list of the hard-coded certificate authorities that the Chrome browser will trust. And they have a team who like audits the different companies who want to be a certificate authority and check to see if they have good processes. And they have some criteria. You have to, pass these audits and like have these processes in place and, make these attestations and, all these criteria. And if you meet all the criteria, they'll add the company to the list. So today it's basically the web browser vendors who we've delegated that job to. Hopefully they're doing a good job. We trust them to do a good job. So some company could spring up and say, I'm a certificate authority now, and start issuing certificates. But if no one trusts them, like, it's just noise. So until some web browser vendor says, okay, we'll accept certificates signed by you as valid, or someone else like accepts that, says, I will accept certificates signed by that company, they got nothing.
Message, signature.
Yeah. Yeah, what do signatures look like in practice, and can you just modify the message without changing the signature? Typically what that would be is like Alice would send two fields. One field is the message and another field is the signature. The signature message is just some bits or bytes. Signature is also some bits or bytes. Typically a signature, it might be 2040-bit long thing. If Mallory changes the message, that will no longer be accepted by the recipient because the signature will no longer be valid. It's the same thing with like a message authentication code. It's like a hash of the message, but it also depends on the private key and done in this fancy way that you can verify without needing to go to the private key. Yeah, so it prevents tampering with a message, because if Mallory wants to modify the message, she would have to modify the signature too somehow. But that depends on the private key. She doesn't know the private key, so Mallory can't know how to modify to make it valid.
Possible to like change the message and at the same time as the match.
Yeah, it's impossible to change the message and the signature at the same time and make them match unless you know the private keys. But if you don't know the private key, there's no way to like change the message and find a matching signature. Same thing with the message authentication code. With the message authentication code, if you don't know the key, there's no way to change the message and find the matching tag. A signature and a tag, it's the same thing. It's just two different words for the same thing. Other questions or discussion? Then let's take a break and then we'll do some case studies. So we'll take like a short 3-minute break and then we'll do some case studies. All right, so continuing from here. Oh, hey, I had something else I wanted to tell you that I forgot I wanted to tell you. I'm remembering now. Besides certificates, certificates are not the only way to get public keys. It's just a really popular way. But there are other alternative models out there. And one that you might run into if you use SSH is sometimes called trust on first use, also sometimes called leap of faith. And SSH has a different model. In SSH, there's no trusted directory. There's no certificate authority. There's no certificates. The first time you connect to a machine, the server sends its public key in the clear, and the client just believes whatever it's been sent. Just optimistically hopes there's no malware present, but remembers it for all future connections. And then for future connections, make sure that the public uses that public key to verify future connections. So the security properties of that are kind of interesting. If there's a malware present the first time you SSH into a server, you're getting screwed. You're getting the wrong public key. You know, sorry, buddy, all security is lost. Too bad. Oh well, cryptography didn't help you. But if there's no malware present the first time you SSH into a server, and then the next day you make another SSH in, and the next day malware is present, that kind of attack is prevented. In that case, malware can do nothing, because the first day we got the correct public key from the server, there was no attacker present. And then the client remembers that public key for all future connections to that server and will not accept anything unless it's been signed, can verify the digital signature using that public key. So the following day, malware starts trying to attack you. Too bad, malware can't get a new public key in and can't forge the digital signature. So this is kind of useful because the intuition for SSH is most of the time we're not being attacked, we hope. Maybe occasionally we'll be attacked, but most of the time we're not. So the first time we connect to a server, probably will be okay. So most attacks that happen will be not on the first time connection. And so most attacks will be stopped by this. There'll be some attacks this won't stop, but hey, it's a lot better than nothing. And it's really easy to use. We don't need any certificate authorities or trusting anyone or signing certificates. It just happens. Kind of interesting trade-off. Very, very practical. Seems to work pretty well in practice. Yeah.
Honestly. Manage the active system, gain control over it. You probably have that system forever. So
the place where SSH uses this is for authenticating the server. So it's really more about defending against like malicious routers or malicious people on your Wi-Fi network, some network-based attacks. It's not really trying to defend you against if the server you want to connect to has been hacked. If the server you want to connect to has been hacked, you're probably toast. Like you're sending your password to that server. If it's hacked, it can store your password. I don't know. It's got all your files. I don't think SSH can do anything to protect you if the server you're connecting to has been hacked. But what it can try to protect you is if someone's tampering with packets sent between you and that server. Or someone's trying to pretend to be that server, but it's not actually the real server. But it's a good point, yeah. There are some kind of compromises that this is not going to protect against. So it's definitely like an imperfect. It's not a, I don't know, solution is even the right word. Yeah.
It's like detect, like you go up like the first time, like the next day you get a different public key, like you move one.
Can I detect? Yeah, if the first day I try to connect to the server and actually there's an attacker, malware is present and giving me bad public key and I don't realize it the first day, and the second day I try to connect and now the server gives me now I'm connecting to the real server and it gives me a different public key. Can I at least detect it? You can. If you try to, in that case, the SSH, when you do the SSH, it will give you an error message or a warning message saying, warning, the public key has changed. Are you sure you want to connect? And then it leaves it up to you to enter whether what to do in that situation.
Like, if the first day.
There's no way to tell whether it was it the first day or the second day that was right. I guess in principle, what they imagine you'll do is you'll like phone up the system administrator and say, hey, can you tell me what the correct public key is? Except, you know, in real life, we're not going to do that. All right, so I want to talk enough about certificates and public keys. I want to talk a little bit about password hashing as an application of cryptography. I want to talk about a couple of places where cryptography is used. One place where it's used is for password authentication. Remember about hash functions. They can hash very large inputs and they are one-way and collision resistant. Okay, so password authentication. Password authentication sounds like a really simple problem. I want to log into a server. I have a password. The server has stored a copy of my password. When I connect to the server, I type in my password and the server checks whether what I typed in matches what it's got stored. Seems really simple. What is there to say about it? Boom. But it turns out there's some tricky bits here. There's some tricky bits. If you code it up in that obvious way, then it does have a little bit of a downside. If the server has a file or a database that stores everybody's password, the downside is if that server ever gets hacked, the first thing the attackers are probably going to do, historically, the first thing attackers do is they download a copy of that password database or that password file with everybody's passwords. And that means the hackers now know the password to every user who can log into that server. If this is like eBay, and the attackers have now downloaded the password for every eBay user, that really sucks. Maybe the eBay system administrators can detect that they got hacked and like, oh shoot, I better patch up the bug and like kick off the bad guys off this machine and like revoke their account and like reformat the hard drive and reinstall the operating system. Phew, they no longer have access to eBay's machines anymore. But they've already downloaded a copy of every eBay user's password. So the attackers can now log into any eBay account of any eBay user. And that is really hard to recover from. What is eBay going to do about that? Invalidate every eBay user's password and like make them all log in again? That really sucks. And even worse, people tend to reuse the same password on multiple sites because remembering passwords is annoying. And so we've seen historically a lot of cases where like some random discussion forum that doesn't really matter very much gets hacked. The hackers download a copy of the password database. They get the passwords for all the users on that discussion forum. And then they start using those email addresses and passwords, trying them on other websites, guessing that those people may have reused the same password elsewhere on other websites, and are often able to get into the accounts on other more sensitive websites. Like their Amazon account, or start like ordering, I don't know, ship me some jewelry or something like that, using the credit card on file. That's not good. So kind of like a toxic waste or pollution on the internet, that one website, this discussion forum that doesn't matter much, get hacked, and a whole bunch of other websites get affected. Or their users' accounts on a whole bunch of other websites gets affected because of the password reuse problem.
Like, doesn't something like Google Auth like mitigate a lot of the password reuse?
Yes, yes. So one solution to that problem is passwords suck. Let's stop using passwords. So like Google OAuth is an alternative so that we don't use passwords to log into this, we use our Google account to log in. And then the discussion forum doesn't have to store any passwords. And so if they get hacked, it doesn't reveal their users' passwords, and there's no like risk to the users and to the other websites. And that would be a great solution. That's a great solution. I want to talk about what to do for those sites that do still want to enable a username password authentication. So over the years, what we've realized is that it's a bad idea to just store the passwords of all the users on your site. The obvious thing to do to try to reduce this risk is to like encrypt those passwords, store them in encrypted form. But that doesn't help. It turns out that doesn't help, because to check whether a user's passwords is correct, you need to be able to decrypt that. So somewhere has to be stored that key. And so if hackers hack that server, they're going to download the encrypted database and also download the key. They both have to be there. So it kind of was pointless to encrypt it if the key is also going to be stored right next to it. It's like locking your front door, but then like hanging the key on the doorknob. So instead, we have a better way to store passwords if you really want to use password-based authentication. And the solution is to use cryptographic hash functions. Don't store encryption of the password, store a hash of the password. And the insight is the server doesn't actually need a way to recover your password. They just need a way to check whether what was entered is correct. Check whether a claim at the password is correct. So they don't store. So instead, what the standard advice today is, websites, servers should not store the passwords of their users anywhere. Don't store the password. Instead, hash the password with the cryptographic hash function and store that hash value. And then when a user wants to log in and enters in their alleged password, the server can verify whether that's correct by hashing what was typed in and checking that hash value against what's stored in the database. Because hash functions are deterministic, if it's the correct password, it'll have a matching hash value. And if it's an incorrect password because they're collision resistant, it'll have an incorrect hash value. So in this way, the server can store information that's enough to verify a claimed password, but isn't enough to like recover the password itself. Because the cryptographic hash functions are one way, a hacker who downloads a copy of these password hashes cannot invert and recover what the original passwords were. So can't come up with the password to use on some other website to try to log in to the Amazon accounts of the people who use this discussion forum. Okay, does this idea make sense? So this is standard advice for how to store passwords on a server. And this advice has been around for maybe 30, 40 years. Except we realized, oh no, there's some problems. This is still not enough. Hash functions are deterministic. So if you store the hashes, if two users have the same password, you'll have the same hash value in the database. And it'll be possible to tell that they have the same password, even though we don't know what their password is. That's maybe not that big a deal. But another consequence is it means that an attacker who has a guess at one of the user's password can verify whether that guess is correct. So let's say a hacker breaks into the discussion forum, downloads a copy of this database containing all the password hashes. Then the attacker can try to run through a whole bunch of candidate passwords. Maybe it's password, maybe it's 1, 2, 3, 4, 5, 6. Maybe it's all possible, like 6-digit numbers. It could be a date of birth. And start hashing each one of those and check whether each of those hash values matches what's in that database. And if there's a match, then the attacker knows that their guess at the password was correct. They have figured out what the password of that user is. So people pick passwords that are like 6-digit values based off of a birth date, a birthday of someone close to them. Then an attacker can try all 10 to the 6 million possible 6-digit values, compute the hash of each, look for matches, and figure out what the passwords of people are. So this is known as a dictionary attack. It's called a dictionary attack because in the early days, a lot of people chose as a password, they would choose a word that was in the dictionary, like giraffe or something. And so the dictionary attack would be run through all the words in a dictionary, try hashing all of them and see if any of those is the user's password. And this is an attack that can be done very efficiently because hashing is fast. You can very efficiently compute the hash of every word in the dictionary or every 6-digit value and check whether any of those are correct. And worse still, a more serious problem still, this is an attack. If I thought that you were using a 6-digit password, I could check that by computing 1,000,000 hash values and checking it against the hash value that I downloaded for you. And then if I wanted to check that for Tanya's account, I could do 1,000,000 more hashes. But I actually don't need to do 1,000,000 hashes for you and then 1,000,000 hashes for Tanya. I can do 1,000,000 hashes once of all 6-digit values, take that list of 1,000,000 hash values and check, merge that against the list of your password hash and Tanya's password hash and all the other password hashes in that database and check if there's any match between these two lists. So I can in one go check all the users of this website to see if any of them have a 6-digit number as their password. So it's very efficient for an attacker to do these dictionary attacks. And if users are choosing passwords, which many users do, then it may be possible to recover their password in this way, even though the passwords are hashed. So just password hashing helps some, but is not as secure as we'd like. So then security people said, okay, aha, I can improve password hashing. What we're going to do is for each user, we're going to pick a random value. It's like an initialization vector. It'll be different for each user because it's random. We call that a salt because someone is just too funny. The hashes, and what do you add to hash to make it even, hash browns to make it even better? You add a little salt and hash browns taste even better. Ha ha ha, so funny. Anyway, so it's called a salt. And when a user registers an account and a password, the system chooses a random value and it doesn't hash their password. It concatenates their password with their salt and hashes that concatenation, and then it stores the salt and the hash value. Then when the user wants to log in again later and enters in what they claim is their password, it's possible to look up their salt, concatenate that with what they claim is their password, hash it, check that that matches the hash value stored in the data. The server can still verify users, authenticate users when they want to log in. The benefit now is an attacker who breaks into the discussion forum, downloads this database of hashed passwords and salts, runs through all 6-digit candidate passwords, hashes all of them, cannot check in one fell swoop all the users. Instead, they have to do a separate check for each user. For Alice, they have to look up Alice's hash and try all 6-digit candidate passwords together with Alice's hash and hash that. That's 1,000,000 hash computation and see if any of those match Alice's hash value. And then can do that for Bob, but it's going to have to do 1,000,000 more hash values because Bob's going to have a different salt. So there's a different value concatenated in. So you can't reuse that computation we did for Alice. We can't reuse that computation to try to attack Bob. Have to do this computation over and over again separately for each user. So that the time for dictionary attacks is increased if the website uses salts. Different users can have the same password and it won't show up as the same hash. Yeah. And even that turns out is not enough because hashes are so fast that you can still do these dictionary attacks. So then people discovered there's an even better way, which is what we should do is we should artificially make our hash function really slow. If it takes 1/10 of a second to compute the hash, that's awesome. No user is going to mind if it takes, they're not going to notice if it takes 1/10 of a second to check if their password's correct. But it's going to slow down an attacker doing a dictionary attack a lot if it takes 1/10 of a second instead of 1,000,000th of a second. And so people have designed artificial hash functions that are designed to be deliberately slow and there's no way to speed them up. And if you want to imagine how you do that, you take a fast hash function I have a fast function. I can compute it in 1 microsecond. That's way too fast. I want it to be slow. What I do is I take the input X and I hash it, and then I hash the result of that, and I hash the result of that, and I hash the result of that, and I do that 100,000 times. And there's no way to like shortcut that long computation. Okay, so that is a method for protecting passwords. It's not perfect. It's definitely still attackable. For instance, the attacker can still do a dictionary attack on each user individually. It'll be slow. They have to compute many of these slow hashes, once for each user. They can't try too many guesses, but if people choose really bad passwords, it might succeed against some users. And the attacker can still try guesses by trying to log in, try and connect to the web server and trying sending a password and see if the web server lets you in. You can still try a few, but you probably can't try too many, maybe 5 or 10 a second or something like that. So if users choose really bad passwords, maybe you can get into some people's accounts, but maybe most of them hopefully are secure against this. So in summary, you can use cryptographic hashing with a whole bunch of improvements to make password authentication more secure, even if the server might get hacked at some point. That said, the right answer today is probably not more and more hashing, but to ditch passwords. Passwords have a whole bunch of problems. People often choose guessable passwords. They reuse them on many sites. We can be tricked into revealing our password by phishing or by scams. They're widely used because they're really easy to understand. They're really familiar. The human factors element is like really familiar to people and also kind of like understandable and like it's not, overwhelming. But from a security perspective, they kind of suck. And so people are working on lots of improvements. You can go read about them on your own if you're interested. There's all sorts of schemes out there to try to address some of the shortcomings of passwords. Like one that I highly recommend to everyone is use a password manager. Don't memorize passwords. Let your browser remember the passwords for you. And let your browsers pick hard to guess passwords. That way you don't have to choose a guessable password because you don't have to remember it. It can be one that's really hard to guess. Another way that's really handy is those websites where don't even bother with a password. We'll just email you a link, click the link, and you're in. That's cool. Although that means if someone hacks into your email account, that's really high impact. So better really protect your email account. That's the root of trust for everything. Another nice one is like two-factor authentication, really good defense. Both a password and you have to hit OK on your phone. Great solution. And how does the hit OK on your phone work? There's an app on your phone with a private key that's generated specific to you that signs something, does some public key authentication, signature, digital signature to verify that you approved and clicked OK. And more recently, we're starting to see some browser vendors and operating systems and websites support a new technology called passkeys. And passkeys are even better way that use digital signatures and public key cryptography to provide very strong security. The idea is that your phone has a private key, might even be stored in some secure hardware. That private key never leaves your phone. And to log into a website, your phone digitally signs something with that private key saying, hey, David wants to log in, right now at this time and so on. Sends that to the website. And the website, when I register the website, I register my public key. So someone else who doesn't have access to my phone will not be able to send an appropriately digitally signed message and won't be able to log in. And trying to guess my password won't help. All right, cryptography is used all over the place in all sorts of other places. I ran out of time to tell you about it, but I hope this gives you a little bit of a feeling what the building blocks are and how you could use them to protect systems yourself. And I hope you have fun designing a secure system in Project 2. Next Monday, I am going to be traveling, so you're going to have a guest lecture from our 2 head TAs, brilliant undergrads who've taken this course, taught this class, including taught it over the summer, been a TA. So they should be really good, and I hope you have a good time next Monday.
The difference between a passkey and a two-factor authenticator?